You know, in physics, we think of the rules as being absolute. But what if there's a hidden rule? A rule that says the universe must always get simpler. Today, we're on the hunt for a single, mysterious number that enforces this cosmic law. It's called the central charge, and we're about to find it in a place nobody ever expected.
So think about it like this. What if physics had a one-way street? A fundamental rule of nature that says things can only ever simplify, they can never get more complex. It sounds a little strange, right? But it turns out physics has exactly that. And it's the principle that's going to set the stage for our entire story. Well, that one-way street has a name. It's called the K-theorem. A great way to picture this is a boiling pot of water. That's a high-energy system, right? The water molecules are just zipping around, super chaotic, doing all sorts of things. But as that water cools down, as it loses energy and turns to ice, those molecules lock into this rigid crystal structure. They have way fewer ways to move around. The K-theorem basically says this is a universal rule. As any system loses energy, its complexity, what a physicist calls its degrees of freedom, can only go down.
And how do we actually measure this complexity? Well, we do it with our main character, the number c, the central charge. The C theorem, in math speak, is just this rule. C at high energy, what we call the ultraviolet or UV, has to be greater than or equal to C at low energy, the infrared or IR. So C is kind of like the scorekeeper for complexity, and the score can only ever go down. But what is this number really? Where does it come from? To figure that out, we have to look at the whole problem in a completely new way. And this is where things get really clever. To truly understand where C comes from, physicists realized they couldn't just look at a system in the usual way. No, they needed a new map, a new way of seeing time and space itself.
And this image right here shows that new map perfectly. On the left, you've got the standard view, a theory that lives on a cylinder, where time just flows up from the bottom to the top. What physicists did was basically the equivalent of taking a paper towel tube, slicing it right down the side, and unrolling it flat into a plane. This little mathematical trick, it's called radial quantization, and it completely changes the scenery. It redefines how we see the whole system evolve.
Now, what's so wild about this is how our basic ideas get completely rewired. On the cylinder, time was just that vertical axis. Simple enough. But on the plane, time flows outward from the center, like ripples in a pond. The past is at the very center, and the future's way out at infinity. And the engine that drives this evolution changes too. It goes from the Hamiltonian, which is basically the system's total energy, to something new called the dilatation operator. This thing now controls how the system scales, zooms in and out. This new viewpoint, this is the key to everything.
Okay, so now we're on this new map, this plane. The next step in our little investigation is to understand the language of this new world. We need to figure out the language of its symmetries. What are the fundamental moves this theory can make that leave the physics totally unchanged?
Turns out these moves are described by a set of mathematical objects called the Virasoro generators, which we label L_n. You can honestly just think of them as a set of dance moves for the theory. A shift, a rotation, a scaling. Each one is a generator that represents a fundamental symmetry.
So for example, the generator L_1, it just does a simple translation, slides the whole system over. The generator L_0 is a little different. It handles the scaling and rotations, like zooming in or just turning the system around its center. Altogether, this whole family of generators, they form the complete toolkit of the theory's symmetries. Okay, so this leads us to the crucial question. We've got our set of dance moves, but what happens if we do one move and then another one right after? Does the order matter? Is a shift and then a rotation the same thing as a rotation and then a shift? In physics, answering that question reveals the really deep structure of a theory.
And all this intimidating math you see here, this thing called a commutator, it's just a fancy way of asking that exact question. It calculates the difference between doing move M, then move N, versus doing move N, then move M. If the answer is 0, well, the order doesn't matter. But here's the thing physicists discovered. The answer is not 0. The order absolutely matters. And the reason why is where our story takes its biggest turn.
And here it is. This is the answer. This equation is the Virasoro algebra. It's the official rule book for combining any two of those symmetry operations. It tells you exactly what you're going to get. And I know, at first glance, it just looks like a bunch of math. But trust me, there is a profound surprise hidden right inside it.
Let's look a little closer. See, the first part of the result is kind of what you'd expect. You combine two dance moves, you get another dance move. But this second term, This thing was a complete shock. It's an extra piece that just pops out of the math. And it's not another generator, it's just a number. And that number is being multiplied by our old friend C. It's like a glitch in the symmetry, a totally unexpected twist in the rules.
And, as the source material for this explainer puts it so well, this is the very reason C gets its name. It appears in the center of the algebra. It's this extra constant term that just wasn't supposed to be there. This mathematical anomaly is the central charge.
So a number just crashed the party. What started as a hunt for a measure of complexity has led us to this really weird glitch in the mathematics of symmetry. But you know, in physics, glitches like this, they're often not glitches at all. They're features. They're pointing to something much, much deeper.
And here it is, the grand finale. The C that mysteriously gatecrashes the rules of symmetry, this central charge, is the exact same C from the C theorem that we started this whole thing with. The number that dictates how complexity has to decrease over time is also the number that measures a subtle break in the system's fundamental symmetries. The two mysteries, they were one and the same all along.
So here's the crucial point. This C is no accident. It's what physicists call a quantum anomaly. The best way to think about it is like this. You've got a symmetry that looks totally perfect on paper in the classical world. But when you zoom way in, down to the weird, probabilistic world of quantum mechanics, that perfect symmetry gets subtly broken. And the central charge, C, is the exact number that tells you how big that break is. It's not a bug. It's a fundamental feature of our quantum reality.
And this number, it's unbelievably important. It tells you exactly how many moving parts or degrees of freedom a theory has. It reveals this deep quantum secret about its symmetries. In fact, for theories like string theory to even work, this anomaly has to be there. The value of C also acts like a fingerprint, which lets physicists classify entire families of different physical theories.
So let's just quickly retrace our steps, right? We started with a simple rule, the C theorem. To understand it, we had to get a new perspective with the cylinder-to-plane map. This introduced us to the key players, the Virasoro generators. And when we finally saw how they played together, we found the twist in the tail, the central charge.
So in the end, the central charge is so much more than just a number in some equation. It's a really deep statement about the fundamental structure of our universe. It connects the flow of complexity to the subtle rules of symmetry, revealing this hidden layer of the quantum world. What started out as just a mathematical quirk, a glitch, ended up being a cornerstone of modern physics. It really makes you wonder, doesn't it? What other beautiful glitches, what other hidden rules are still out there, just waiting to be discovered in the fabric of our reality?